Now we're going to work with an example over here where we have to apply the alternating series test to show that a given series converges, and then we need to apply the alternating series estimation theorem to find the sum of the series with an error less than the number given. So let's begin by checking that. Let me write the series here again. Let's check that this is actually an alternating series. So we are summing from 1 to infinity. We have the factor -1 to the power of n plus 1, and that's being multiplied by 1 over n to the power of 4. So since this 1 over n to the power of 4, this will be our an, this is always greater or equal than 0, actually it's greater than 0. This is in fact an alternating series. To prove that it converges, we are going to show first that the limit of the an terms over 1 over n to the power of 4 as n approaches infinity is 0. Okay, yeah, that's true. And then the other condition we need to verify is that the terms of the an sequence are decreasing, and that's also true because we know that the reciprocal n to the power 4 is increasing. So we verify conditions A and B from the alternating series test, so the given series converges. Now we would like to look at an estimate for the sum. We cannot find the sum, but we want to know up to which partial sum we need to consider to make sure that the error is less than 0.001. And let's begin by noticing that this 0.001 is actually 1 over 10 to the power of 4. This is by definition the term A10. So from our alternating series estimation theorem, what we know is that the sum of the series minus the term the term 9 of the sequence of partial sums in absolute value is less or equal than A10, which is the value 0.001 that we want. So that means that to have an error that is less or equal than the number we want, we need to look at the term number 9. I mean the term number 9 of the sequence of partial sums. So we need to sum from n equals 1 to 9. And then we have the factor -1 to the power of n plus 1 times 1 over n to the power of 4. So let's find the value of this in the calculator. So the partial sum we're trying to find is giving us this result. Let me copy it. And it goes over here. So what we are saying is that when we are approximating the value of the sum with this value found here with the calculator, the error is going to be only in the 1, 2, 3, 4 over here. Yeah, the fourth decimal place over there, there could be an error of plus minus 1. So that means that this result, which is 0.947 correct to 3 significant figures, is actually a correct to 3 significant figures approximation of the sum of the series that we are considering.